Hello everyone, welcome to today's webinar, and in this webinar we're going to talk about secure by design, updates and evidence by architectures and what they mean for the CRA. So our goal is to walk you through the process of preparing secure by design IoT system using a combination of hardware and software security features, and the focus will be on more simplicity and ease of use, making it easier for you to understand the requirements of the CRA. So let's get started. Before we dive into the CRA and security, a quick word about who we are. We are a know-how partner, and we've been focused on embedded system training and support for more than 20 years. We are not a general IT company, so we've been living in the world of microcontrollers, system on chips, and low-level software. Our catalog today has over 150 courses covering RTOS's Linux, security, FPGA, C and C++, and more detailed architecture trainings. So a little introduction about myself. I'm Ayub Bojila. I'm a training engineer at AC6, where I focus on RTOSes and embedded security. I spend most of the time helping teams bring up microcontrollers, harden their software, and make sense of any new security requirements like the CRA. I have a PhD in embedded system from the University of Lorraine here in France, where I worked on low-level implementation and embedded design. So today my role is to design and deliver trainings and consulting missions on secure embedded system. That's the experience I will try to share with you during this session. First of all, we are going to talk and define the scope of the CRA, why the CRA matters. That's the first topic we are going to cover. Then next we are going to see a definition of secure by design and evidence according to the CRA. Then later, how to use the secure by design and how to use the evidence by architecture in conformity assessment. And later we are going to talk about a very hot topic, which is provision and secure updates, where I will show you some examples based on an MCU configuration. And finally, we will wrap up with a conclusion, summarizing the key points and addressing any questions you might have. So why CRA matters? Of course, it's an obligation. So I'm going to use the Linux Foundation study about the CRA that you can find here in the link in the PDF that will be shared later. So what was stated in the report is that awareness is still low. So most organizations are only slightly familiar with the regulation, and more than half are unsure about the deadlines. So a large number of manufacturers, they rely passively on upstream open source projects for security fixes, while only minor or minority produce SBOMs or have a proper dependency tracking in place. So we also see a gap in roles and responsibilities between system integrators, consultants, academics, trainings. They don't neatly fit the CRA definition, and many stewards lack dedicated resources for incident response. At the same time, this regulation is expected to increase costs, of course, roughly around 6% average price impact, and companies highlight legal complexity, component safety, and supply chain risk as major concern. All of this explains why the CRA preparation is uneven today, and why building clear process automation and secure by design workflow is becoming essential for everyone involved in connected products. So first of all, let's fix the scope of the CRA. The CRA affects a lot of organizations, but its focus is narrow. It's about the security or cybersecurity of any product with digital elements. So hardware plus software products, not generic services. It does not cover non-commercial tools, hobby projects, or pure website services where there is no product being placed on the market. It applies to any PDE that is available in the EU market, including connected devices and software distributed here, even if the manufacturer is outside of the European Union. So some sectors are handled by their own regulation, like medical, like automotive, like automotive. For example, 26262, they have their own cybersecurity regulations. So if you ship a connected product into the EU, the chances are high that the CRA applies to you. So how it applies? Here we have a milestones of the CRA. So the regulation officially entered into the force on 10 December 2024. We are nearly 1 year later. So the next big step is June 2026, when the member state must notify the conformity assessment bodies. Then on 11 September 2026, we will have the Article 14 that becomes active, meaning that manufacturers must start reporting vulnerabilities. And finally, 11 December 2027, this is when the CRA is fully applicable, and all essential requirements and obligations must be met for any product placed on the EU market. So we are already inside the transition period, and the technical work really needs to start now. You will notice also something that I didn't mention here if you've been around the CRA, that is not included. For example, the horizontal standards and the vertical one, like the horizontal standards CRA, PT1, PT2, PT3, I will talk about that later. They are expected to be published between 2025 and 2026, which is the case, with drafts circulating earlier. So these will give the technical interpretation of Annex 1 that define the technical requirements. And after that, we will have the vertical product specific standards. They will follow. They are technology agnostic, so they are very dedicated, specific to devices that are in important class 1, important class 2, and critical, and they are likely to be available in October 2026. So these will cover, as I said before, families. They can cover IoT devices, industrial controllers based on the category, and we will have one standard per device. So they will land before full application in December 27, and they will shape the conformity assessment for many PDEs. So these are the key annexes of the CRA. The parts that we constantly refer to when designing, documenting, and assessing a product is Annex 1. Annex 1 is the big one, which has essential cybersecurity requirements. It tells us how the product must behave from a security point of view. The Annex 2 will describe what must appear in the EU Declaration of Conformity, this document you sign when placing a product on the market. Annex 3 explains how products are classified, important, critical, or OSS stewards, and these classifications will affect which conformity route you must follow. The Annex 4 lists the critical products with digital elements that automatically fall into higher scrutiny, and the Annex 5 and Annex 7, they define the conformity assessment modules, basically the different paths manufacturers can use to demonstrate compliance, including third-party involvement for some categories. So together, all these annexes, they form the structure that guides both engineering work and the compliance process. So these are the key actors that are defined by the CRA, each with different duties. We have the OSS stewards, which is the organization that manage open source projects. They fall under the CRA too, like for example Zephyr project or Linux Foundation, FreeRTOS, and others. The OSS developers, meaning individuals contributing without commercial intent. They generally exempt unless their work becomes part of a commercial chain. The manufacturer is the most important role. This is what we are going to focus on today, is the entity placing a product with digital element, as we explained before, in the market under their name or brand. They carry full responsibility for compliance. They have to do design, risk assessment, documentation, CE marking, everything. And if the product is made outside of the European Union, I should use that word, the importer, he takes full responsibility for verifying that the manufacturer has met all obligations and the technical documentation exists. And finally, there is the distributors. This is just companies that are selling PDEs in the EU without modifying them. They must also check that we have CE marking on those devices. They have instructions, and the product is compliant before putting it on shelves or selling them. So understanding these roles is essential because CRA obligations depends on who you are in the supply chain. So I do like to show it like this, depending on which type of product you are, the extensive requirements go up. So you can see it as like a temperature here. So if you are in the minimal requirements, it's too low. If you go up to the extensive requirements, you are in the critical product, so you have a lot of things to do. So I recommend you to check the annex, I think it's annex 6, sorry, yeah, where you have the important class 1, 6, where you have the important class 1 and the important class 2. Default products, they are non-classified PDEs. So these only need to meet the core CRA security requirements and basic reporting. Above that, you have the important class 1 and class 2. These requires additional documentation, stronger vulnerability handling process, and in some cases more rigorous conformity steps. And at the top, you have the critical products. If I remember well, it is written there, it's Annex 4. These undergo the most extensive requirements, including strict conformity assessment and third-party audits, plus a lot of things that has to be done. You know, when you do the conformity assessment, you have multiple modules that you have to assess based on your product category. So the higher the classification, the heavier the obligations. and knowing where your product sits determines your entire compliance path. So the European Commission defines the regulatory objectives and issues standardization requests between SENS, LEC, ISO, IEC, then translates those objectives into technical harmonized standards. Once a harmonized standard is published in the official journal of the EU, manufacturers who follow it gain presumption of conformity, meaning their product is automatically considered aligned with the CRA requirements, and member states support this process throughout market surveillance and by identifying what are the needs for new standards. So in practice, the harmonized standards, they will become the technical playbook for compliance. They will tell engineer teams exactly what we are waiting for them, from them, and what are the things that we should implement for the CRA. So yeah, around typical pitfalls that we see, these are some of the most common CRA pitfalls we see in the industry. First is the scoping too narrowly. Teams sometimes focus on the application but forget that the bootloader, firmware, cloud backend, and companion apps, they are under the CRA. All of these fall inside the system boundary. Second is treating the open source as if it were outside the CRA. So if you use OSS, you still need an SBOM, you still need to do vulnerability tracking, you still need to have a clear maintenance responsibility. You can't assume upstream will fix everything for you. And third, ignoring legacy devices still in the field. So if they are supported, Article 14 still applies. You must handle vulnerability and provide updates during their support lifetime. So these issues appears again and again, and fixing them early makes the CRA compliance much more smoother. So now let's talk about the secure by design and evidence. So I was saying that we are going to see the PT1, PT2, so I'm going to give you an overview of it. Article 13 of the CRA requires that any products with digital elements placed on the market is designed, developed, and produced in line with the essential cyber security requirements of Annex 1 that we will see later. It also requires a cybersecurity risk assessment, and that its results will guide us through the entire life cycle, which is design, development, production, and of course, design, development, production, delivery, and also maintenance. So to support this, as we explained before, there is a standard framework that is being built around the CRA, PT1, PT2, and PT3. PT1 covers the general principles for cyber resilience, which is the secure by default or secure by design mindset. PT2 defines how to implement the Annex 1 cybersecurity requirements, and PT3 defines the vulnerability handling in line with Annex 1, Part 2. So this translates into our development workflow. So we start from the product risk assessment. This is the first thing that we should do. Then we implement the essential requirements. Based on that, we define the update, for example, and vulnerability handling strategies, and we capture any evidence at every step for conformity later. And during maintenance, the same structure is used to handle the vulnerabilities and reporting consistently. So PT1, PT2, and PT3, the horizontal standards, describes what must be achieved. The next step is understanding where these obligations sit in our day-to-day engineering lifecycle. So I didn't talk about the vertical one. They are still in draft. You can see in the Etsy website, there are a lot of them are available. So you can take a look to see what's going on, what they will be. There is also some working groups that are available. So if you have some questions, you can join them. So yeah, if I want to summarize a little bit the CRA, I do like to show it like this wheel maps the CRA obligations here. So it maps it into multiple parts. So we have multiple steps: the analysis, planning, architecture, design, software development, testing, deployment. So these are all the steps or stages. And this is not just legal or compliance. For example, the analysis, this is where we perform the cybersecurity risk assessment for the PDE. Planning, this is where you choose which standard tools and process that you are going to use to meet with the Annex 1, including PT1, PT2, PT3. The architecture design, this is where we select the CPU, system on-chip security features, the RTOS that you are going to use, the trusted firmware module for the Cortex-M that we are going to use, the update path. This is where our secure by design decisions will be locked in. Software development, this is where you implement your secure coding rules if you have some, and the correct configuration. You generate artifacts that becomes later your CRA evidence. The testing, very good subject. This is where you show evidence of testing. You run functional and security tests to ensure that there are no known exploitable vulnerabilities at release. The deployment, also very, very big subject. How do you provision the keys? How do you enable secure boot? Do you configure any updates, where they are? How do you monitor them? And this is the start of the product, CRA live in the field. So the CRA requirements, they span like every role. They span the entire loop, and every role will share his parts of the obligation. So of course, in this session, we are going to focus on step 3, 4, and 6, which are the architecture design, the software development, and later the deployment, just an overview of it. So here we are going to try to turn the Annex 1 into something engineers can actually use. The idea is simple. Treat the CRA essential requirement as a design time checklist. So we start from the product risk assessment, device, sensor, gateway, app, and remote data processing. By the way, they are all part of the PDE. So they all must meet Annex 1. Then we check that our architecture delivers the key outcomes, which are secure by default, no known exploitable vulnerability at release, authorized access, etc., confidentiality protection, integrity, security updates. These are also has to be implemented. So this secure by design in CRA terms turning legal requirements into a concrete design rules that engineering teams can verify, because we will need to test that later, because you show evidence of something that you are implementing. So in the test you have to show that exactly it was implemented. So before we dive into the architecture, it's very good to have just a lightweight threat model, something very simple enough for us to continue the conversation or to continue the discussion on this. So our scope today will be the device itself. We are not going to talk about the application software. This is other subjects. We are going to focus on the device itself. So we have to keep 3 questions that I suggest you here. What are we building? What are we protecting? Against whom we are protecting this? Through what? So what are we protecting? For example, can be firmware, keys, secrets, safety, availability, or IP. Who are we defending against? Can be remote attackers, insiders, supply chain manipulation, physical attackers if the device is accessible through something, and also through what attack paths, because we need to know in which interface we are going to have the attack: network interface, debug ports, the update process, third-party libraries, some weak default parameters that you have. So from this, we turn the risk into a simple design rules. For example, we can say that no unauthenticated network surfaces. We disable that. There is no debug. The debug is disabled on the field units. Updates must be signed. Tasks isolated by somehow trust zone that I will explain later with the MPU. And the attack surface is kept minimal. This is something that we can use as design rules. So the point here is that the CRA does not require a heavy formal modeling, but it does require just a clear threat model that drives the architecture and secure by design decisions. So we can use STRIDE, that stands for spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. So this is like specific. You can use the DREAD one. There are a lot of threat modeling that you can use. So this is part of how we assess our device to know exactly where the problems that we need to solve later on security are, following the requirements of Annex 1. So now it's time to see a little bit the decisions that we need to lock in early if we can. So for example, I took here, I need microcontroller in my device. This is an IoT device, so I'm going to think about something that will use less power, has more low power features. And so I took the Cortex M33. Why specifically the Cortex M33? Because he has trust zone support. So with the ARM v8 and trust zone, we can get 2 capabilities that are very important, which are the hardware isolation and the software isolation. So the hardware isolation, this is where the processor enforces a split between a secure word and a non-secure word. So this will let us protect any keys, cryptographic operations, secure bootloader, firmware update verification, and other features. So these elements, they will stay isolated even if the application side is having an attack or compromised. There is also software isolation. This is combined with the MPU, which is the memory protection controller or memory protection unit. And we can also have some peripheral protection controllers, commonly named PPC and MPC for memory. So these can be implemented down in the system on chip that we are going to see later. But this is what we can use. So the advantage of having the software isolation, this we can reprogram it. We can do it dynamically. We can change the parameters based on some temper operations. We can do a lot of things in software. So it's completely open and available for us. And we can do that only if we are in secure domain. So for the diagram that you have here, this is an example from ARM showing how the product must be designed like by NXP or SC vendor. So for example, we know that the ARM v8 has a support for trust zone. So there is something that should be implemented by the vendor. It's the IDAU, which is the implementation defined attribution unit. This is where you are going to say, oh, this memory region is secure, this one is not secure. Your bus is under HB5 interconnect. So this one supports trust zone. So every time the processor does something, we know which state he is. So behind it, you can see that there is the MPC, a memory protection controller. So this one is meant to protect the memory. So whenever there is non-secure access to a secure memory region, we have a reply on that. So either we ignore the access or we can generate a fault. And this is configured by the system on-chip vendor. Behind that, you can also have some peripherals that are behind the peripheral protection controller. So we can ensure, as you can see, by hardware, we can ensure that there is some isolation. And all these parameters are configured by the IDAU and also by a mechanism that will be implemented. For example, for SC, they have the GTZ-C, which is the global trust zone controller, that has one objective, is to say this peripheral is secure, this one is not. Even we can go down into the GPIOs and say this GPIO is secure, this one is not secure. So you see, the CPU architecture is very important because we can show a lot of things that are needed by the CRA. We can, by choosing the CPU with trust zone and we have a proper hardware isolation, we can lock in the protection. So we can say that, well, we have a very good architecture security. And yeah, second part, here I want just to go a little bit deeper on a very specific subject, which is the ARM Trusted Firmware M. So the ARM Trusted Firmware M, it used the hardware isolation of the Cortex-M33, which is trust zone, to create a structured, secure execution environment. So the idea is that we can use the TFM to implement authorized access control, confidentiality and integrity, protection for code and data, and isolation for security and relevant resources. So the TFM will give us a reference architecture that satisfies these requirements by construction. Without going too deep into this, just to let you know, we can put our operating system here, and behind it we can have our secure services. By the way, all of them are separated and isolated, and everything is managed by a secure partition manager that will, every time we need to do something or we are going to jump to here, then from there we are going to route directly into which secure service you want, and all of them are isolated. So even if one secure service is compromised, does not prevent the others from running. And this is part of the MILS architecture, so it is implemented in the TFM. Second part is to use a very good system on-chip security. We have, for example, here as an example, the MCX N series with the dual Cortex-M33 that implements a lot of security features, including the edge lock, including the AES, the RSA crypto engine. There is a TLNG. There is a lot of hardware crypto accelerators that we can use later because we need them to secure the communication. We need them for sign-in operations with very strong performance and low power features. Of course, because we need also to manage if the device is off, how are we going to detect any tamper intrusions. So this is very important. So this has to be done in the system on-chip security. So the system on-chip security decision is very important also from the CRA side. It's not just a hardware component, it is the lower layer of our CRA evidence. So now that we covered the CPU architecture, okay, you can use FreeRTOS, you can use Zephyr, you can use other type of operating system. Today my focus will be on Zephyr. Why Zephyr? Because it has a lot of security features that are available, and also because one of the known one, it is CRA style requirements implemented directly. So this is why we choose here Zephyr as an example for this. Yeah, this is how we chose Zephyr as an example. So Zephyr supports something that is named user space. So this user space, it is an MPU-based isolation. So we have user space execution, and we can do a fine-grained permission control between threads and subsystems. So this will allow us to reduce the attack surface, prevent compromised tasks from touching sensitive memories, and also enforce the requirements on integrity and authorized access. Zephyr also integrates MCU boot. So we get authenticated firmware images, signature, verification, anti-rollback. We can also do some safe swap override updates. It's open source, we can use it. It is part of the trusted group, so we can really use it. And supports also the TFM that we explained before. So Zephyr works natively with the TFM on Cortex-M33. So you can route sensitive operations like crypto secure storage, attestation, firmware update verification into directly the secure partition manager. Zephyr supports network stacks. So we have TLS, CoAP, Bluetooth security. All these features are included. It is hardened by default configuration. Why? Because by default, the configuration of Zephyr is secure agnostic. So we know exactly what are the problems. So we disable, for example, very low cryptographic support. It's by default. And of course, as I explained before, it is like, this is one of the strengths of Zephyr. The use of kconfig. In fact, it allows you to build the minimal attack surface controlled images. So you can trace exactly which components are included, generate SBOMs, validate configuration for conformity. This is why we see Zephyr as a CRA enabler. Because if you combine all of this, you will end up with an architecture that naturally supports CRA essential requirements and can generate evidence you can use in the conformity assessment. So the RTOS is not just a scheduler, it is also the glue that will tie your hardware security or your hardware security, with the CRA compliant architecture. A very big subject, which is the testing. Here I'm just giving you an overview about it. So with the security testing, we can have secure configurations that we are going to show if they are implemented or not. We can use some static dynamic analyzers. You can use Z-test, which is a very good feature in Zephyr. So Z-test is the Zephyr's native unit test framework. It gives us a repeatable automated unit and integration tests that can run on real hardware or can also run in simulation like native sim. So we can verify correct behavior of secure services. We can correct enforcement of security policies. This will provide us both functional evidence and also can help us for the documentation that will be mandated later on Annex, I think, 7. So we have also the fuzzing part. So fuzzing, CRA expect manufacturers to use testing methods that can detect security issues. Fuzzing is one of them. So we can do protocol fuzzing, API fuzzing, input mutation testing to reveal any new memory corruption or crashes or unexpected behaviors. We have also the SBOM vulnerability scanning. If you use, because Zephyr produce an SBOM in SPDX or CycloneDX format, we can track all third-party components and libraries included in the firmware. You can also check the OpenSSF ecosystem. They have a lot of tools that are all oriented throughout security. So they have CVE. We can check the CVE associated with the dependencies. We can do a lot of things in testing. So I'll let you check the OpenSSF example. So why all of this matters? Because the CRA is not about doing a single penetration test. It requires us to do a continuous and systematic approach to vulnerability identification. So the combination of secure configs, static analysis, tests, fuzzing, and everything forms a complete testing ecosystem that meets our expectations. So testing is not just a final step. It's a continuous vulnerability handling capability that enables CRA compliance. Finally, of course, the updates. We are going to cover that later, but just to let you know, we discover a vulnerability here, so we need to rerun the testing again, fix, of course, then rerun the testing, then do the update. So the correct order, if I want to follow the CRA by default here, is detect, assess, fix, verify, deploy, then notify. So yeah, every security decisions we make today becomes tomorrow's conformity assessment documentation. So we have, for each decision, we are going to say why and when it was done. So what we decided, we are going to use the MCU secure boot plus internal key storage, why, threat model link, how it is implemented. And of course, for each early decisions, we are going to define that. So this is part of the technical documentation. So why we decided, what risk does it mitigate, which threat in our model does it address, how it is implemented, which modules, which config we did use, which memory regions or peripheral, which tooling we are actually using. So we maintain a small set of living artifacts. Can be a one-page threat model, can be a root of trust and key hierarchy diagram, partition diagram. I will show you more about that later. So this is all part of what we can use as a evidence. So CRA has a second major pillar, which is just as important as the technical work itself. We must provide or prove what we did. So CRA does not only ask, is your product secure? It asks, show me the evidence that demonstrate how you achieve security and how you maintain it. And this is where evidence by architectures comes in. So when we move to the Annex 7, which defines the content of the technical documentation, the CRA becomes very explicit on that. Especially for manufacturers, they must provide documentation that explains what the product is, how it is built, how the security measures are implemented, and how vulnerabilities are managed during the product lifecycle. So the CRA requires a general description of the product with digital elements that will include a lot of things. For example, the intended purpose, the software version affecting the compliance, etc. I'm not to state all of them, but it is well written, defined, and we are going to use that in the documentation. There is two sections, by the way. This is first section, this is what I was describing, and the section 2, this is the heart of the CRA evidence. It requires a description of the diagram, development, and production of the products, including system architect diagram, how the components how the components integrates, where security measures are placed, how essential requirements from Annex 1 are fulfilled, and the vulnerability handling process, the SBOM, the disclosure, the update strategy, and the production and monitoring process. So of course, one example of the evidence that we can show by architecture is what you see here. So as we locked before the MCX N series with the Cortex M33, we can show that we are actually using the TFM, we have trust zone, we have our non-secure word and secure word, all the transitions from the secure and non-secure that are verified, we are using the PSA APIs and secure services, and behind all of this we have the CPU and system on-chip security layer that will provide us with secure boots, with device identity and keys that are certified under common criteria. If you follow the MCX N series, they are under EAL 6+, so this is very good for certification, especially for security. And of course, we don't forget about the connection that we will have with the gateway, with cloud backend, and how it is done. We are going to use Zephyr, so we are going to use the TLS part with the hardened configuration. So we can show evidence by architecture, as we explained, why it matters, because I did use just a simple reference design. So in my example, I was using MCU boot as the secure bootloader. So we can have secure domain and we can implement that. It is part of the Zephyr application. So the Zephyr application will run in the non-secure domain, and optional TFM secure services, we can use them for the secure storage and for the secure update. We can do that. So when we map this into the CRA requirements, only trusted code runs So this means that signed Zephyr images are verified by MCU boot. Secure update mechanisms, MCU boot image swap and rollback. We limit the impact of compromise. So non-secure Zephyr app are separated from secure services. And of course, we show evidence that we can export. As an example, kconfig fragment that I am actually using MCU boot, what are my trust zone setup, the build output and everything that I can use to show the evidence. Partition map and memory layouts diagram. This is the example I showed you before. Test logs from an OTA update and rollback scenario. So all this will give you. So this is why the architecture matters, because it gives us a clear, auditable evidence for Annex 7. As we talked before, our scope was the device itself. So we've done the proof of concept. We've done it on this device, on this board, using this architecture and the operating system we've seen. So everything works. The real question now is what is next, especially for production. Annex 7 does not stop at the prototype. The last part that you see here, it's necessary information and specification of the production and monitoring, etc. So monitoring process, of course. So how the keys are provisions on every unit? How do we handle mass production? What infrastructure do we use for flashing, securing, and validating devices on the line? So all these questions we have to answer to them. And this is why we have the provision and secure update section. This is where we are going to introduce the provision and secure updates. I'm going just to give ideas of what's available in the market. So once we move from the proof of concept to real production, we suddenly need three things. We need secure provisioning, we need mass production, and we need a proper key management. For example, a lot of questions are to talk about here. Let me take you to one. Do you use one key? Of course, we don't do that. What is the best thing to have? One key per device. How you save that? How you store it? When it was provisioned? All these questions we have to answer to them, and we have to provide them as part of the conformity assessment. So maybe you are using one key per batch, or that depends on your risk assessment, how it was done. So of course, we are not going to start from scratch, and all this must be done in a way that matches the CRA expectations for secure manufacturing, meaning that we need to protect the root of trust from the very first unit coming out of the line. So this is where I'm showing here as an example the NXP SPSDK that will help a lot, because it gives us a scriptable framework, Python scriptable framework that we can use in order to generate and manage keys and certificates. There is trust provisioning. You can see here tools, secure provisioning, mass production tools, and third-party tools integration. We can integrate that with other services, AWS if you want, and other services that we can include here. So this will help us to, as I said, to generate and manage keys, to provision device securely, to lock down any secure debug. We can implement debug authentication. We can support the MCU bootloader with MCU boot. We can have a serial download protocol that we can use, etc. So the SP SDK essentially bridges the gap between development security and manufacturing security, which is exactly what Annex 7 asks us to document for the CRA compliance. If you want a cloud-based solution, they have also the edge lock to go. This service lets us generate and manage keys, certificate, and secure objects in the cloud, and securely inject them into the device or devices throughout their life cycle. So you can think of it as a KMS. You can think of it as a KMS plus provisioning. So the infrastructure fully operates by NXP, which gives you a secure, zero-touch, and flexibility for field updates. Our goal is to deliver security updates without breaking the device. So the update process has to be tough enough to survive things like power loss, bad connectivity, a half-written image, or the user unplugging the device at the wrong moment. So even our own security, even if this is not really related to the CRA, but this is we have some concerns on the updates. So even our own security checks, they might stop an update, and the device still needs to be handled or to handle that safely. So the easiest way to think about is what happens if the update fails, and how does the device recover to a known good state, which is covered in, for example, the MCU boot with Zephyr that I explained before. So here I try to show you an example of the requirements on Annex 1, which says ensure that the vulnerability can be addressed throughout security updates, including where applicable through automatic security updates that are installed, automatic of course, that are installed within an appropriate time frame enabled by or as default setting. And what you can see here is my process to prove that. So here we can see how the secure update flow is going. For example, we start by doing a build and sign. You can use the CI here. So in the CI, we build the Zephyr image, we generate the SBOM and sign the firmware. We have an OTA service that does the updates, and on the device, the Zephyr app will download the update into the secondary slot, and after reboot, the MCU boot will verify the signature, check the verification policy, and then do the swap, or overwrite, of course. MCU boot can do also rollback automatically to a known good image. So this update pipeline is exactly how we meet the Annex 1 parts. The Annex 1. So we can deliver trusted updates, distribute them securely, and of course we did use an OTA update service. It can be, for example, Goliath, Hawkbit, Update, Hub, Mender, and others. So you can use also Edge Log2Go from NXP. So in short, our updates trust chain is built on 3 pillars: signing, versioning and rollback, and of course, versioning and rollback. This is the 3 pillars. So for the sign-in, we can say that only our code runs. Versioning and anti-rollback, we never go back to a weaker security level. And the rollback recovery part, if a bad update happened, does not break the device. So if we document these choices clearly in the architecture, we have a solid story for the CRA. Security update, control keys, and a guaranteed way back to a known good state. So this diagram here shows the basic 2-slot update flow. So the device boots into the bootloader, checks whether it needs to recover or not, check if there is a new firmware version available. If not, he's going to jump to the primary slot. When he jumps to the next reboot, so we have the OTA procedure here where we are going actually to download a new firmware version and store it in the secondary slot, and then we reboot. So when we reboot after that, on the next reboot, the bootloader will see the new version, he will verify it and swap it. So if anything goes wrong, the bootloader can fall back to the known good firmware because we didn't erase the first one. But this means that you have enough memory space to handle this. Of course, it comes with a cost. This is what I explained at the very beginning when we defined the CRA scope. So now we are going to move to the conclusion. So we've talked about a lot of things. We've seen why the CRA matters, examples of security by design. And of course, we didn't cover everything on the CRA. So we still have very important topics that we can discuss, which are the analysis, how we do the planning. It is all defined in the CRA with good way to do it. Of course, we covered the architecture design, just an overview of it, software development, and the deployment. So there is also the big part, which is testing, how you provide the testing, how you do the testing. So the goal here was to show you that the CRA isn't an extra layer on top. It's something that we build into each stage of the lifecycle and to provide you with an example implementation. So the CRA turns security into a concrete obligation. So we have to design, develop, and produce products that meets the risk level. This is what we've seen before. Secure by design, this is where we win or lose. So we decided to use some specific CPU and system on-chip security. You can think about also if you work on processor families, we can talk about V8A architecture that has trust zone for Cortex-A. You need to implement something in secure monitor. You can use it in bare metal or by using Linux. You can implement Opti. There are a lot of things that we can cover there. And of course, showing evidence of testing and how the SBOM is used. There is also the provisioning part. I used one from NXP because it gives exactly the answer I want on the CRA. You can find the same one on Retisas, on other vendors. And of course, we can use Zephyr and MCU boot, which is very great because it is not agnostic to any hardware. So we can use Zephyr and MCU boot and guarantee that any type of vendor, we are going to cover that. And we are going to cover the same level of security, if it is based on the same CPU architecture, of course. The result is that we have seen here a reference architecture and workflow, a small one, that you can have in your own CRA compliance story. So what is next? Of course, if you want, you can use the Freedom boards to try Zephyr and do this. Of course, we have also our security trainings, the Cyber Resilience Act, the Secure C++ development for project managers and software developers. And of course, if you want, we can also have a comprehensive Zephyr training. So thank you for your time. And